Hello, everyone. We are starting Chapter 9, and Chapter 9 has two main topics that we need to discuss. The first one is center of mass, and the second is linear momentum. And what center of mass is going to do is it's going to allow us to take a system that has more than one mass in it. This could be a system of two masses. It could be tens of thousands of particles, or it could be a system that is made up of a solid, but that solid material is in turn made up of individual particles. And if we can somehow figure out where the center of this mass system exists, then we can eliminate all the individual masses from the system and replace them with one equivalent mass that will behave in the same manner as what the total system of particles did. And the reason that we want to do this, the reason we want to find an equivalent mass, is so that we just have one physics expression that we're dealing with, as opposed to having to deal with each individual particle on its own. And this becomes even more important when we have solid objects. If we can treat that solid object as just one mass, which is actually what we've been doing throughout most of this semester, we've just been treating every mass as a single object. But what happens when that mass starts to become more asymmetric in its shape? We've typically worked with objects like a ball that drops, and that ball is fairly uniform in its construction and the way that the material is spread out through that ball. But compared to, say, a person does not have their mass equally distributed throughout all portions of their body. And so we need to consider how that mass distribution is going to affect how the object as a whole is going to move and accelerate, change velocity, etc. And the first step in doing that is to equate the entire system down to a single point in space. The way that we're going to do that, and we're just going to jump right into an example problem. We will have an X and Y axes, and each of these tick marks can be of whatever unit that you want, really. If we need to, we could call this, well, we'll just go with meters. The units really aren't going to matter in this case. But for our system, we are going to place three different masses in the system. The first one I'll place right at the origin. That'll be mass 1. The second one I will place right here. And the third one I'll place right out here. So mass 1, mass 2, and mass 3. We will assign some values to these masses. We'll do 1 kilogram, 2 kilograms, and 3 kilograms. By looking at the placement of these masses, we can also assign ordered pairs for the XY coordinates for each mass. Mass 1 is at coordinates 0, 0, since it is at the origin. Mass 2 is at approximately 2 and 6. So we'll put those in. 2, comma 6. Mass 3 is at 1, 2, 3, 4, 5, 6, 7, 8, comma 3, or at least that's what I was intending it to be. We'll move this. We'll move mass 3 up just a smidge so that it's actually at 8, comma 3. And we want to know where the center of mass for this system is. So one way to think of this is if anyone watching the videos has ever worked in food industry before. So you might be carrying out a tray with some food items on it. You know, maybe there's a drink, and over here is a salad, and then you've got an entree. And each of these items is going to have a different amount of mass. And in order to balance that tray, there is a certain location underneath that tray where you're going to have to place your hand if you want to balance all of the masses. And that balance point is the center of mass for the system. Now, the name itself, center of mass, kind of implies that this balance point needs to be in the center. But if our masses are not of equal values, hence the 1, 2, 3 kilograms, we can't expect the center of mass to be at the geometric center of the system. Back in geometry, there are ways of essentially mapping out a point in space that is equidistant from all other points. And well, if we were to try to measure out what would be the center point of this system of masses, it might be right around there somewhere. But that's not going to be the center of mass for the system unless all three of the masses were the same values. And that's not what we have. If you were to be carrying this tray of food out to a person that's going to be eating it, you might have your entree, which, you know, maybe there's a steak with some potatoes or something like that, and then you have your salad plate, which is going to be probably fairly light in comparison to the meat and potatoes, and then you'll have a pitcher of water, which water actually carries quite a bit of weight to it. And so if you wanted to carry this tray out and not spill anything, you would probably have to place your hand closer to the water and plate. Otherwise, it's going to tip over and you're going to spill everything. When it comes to the way that we've laid out the masses, it makes sense that the center of mass for the system should be closer to the larger mass in the system. So instead of having our center of mass right at the center point of the three masses, we're probably going to have to shift it over closer to the third mass. Now there's a way that we can narrow down the expected region where our center of mass needs to be located. And I've already done that in a way. I've drawn a triangle out of the 3 points. And it makes a lot of sense that the center of mass for this system should be somewhere inside that triangle. It should be somewhere centrally located amongst the system of masses. But we can do even better than this. Let's take mass 1 and let's bisect this triangle. So we'll draw a line that goes to the midpoint of the line that connects masses 2 and 3. And let's just ask ourselves, what side of that line should we expect the center of mass to be on? And the reason why we've bisected this triangle is because, in effect, we end up bisecting mass 1. So mass 1 contributes equal amounts of its mass to either side of the triangle, but which triangle now has more mass on it? Is it the side with mass 2 or the side with mass 3? And it's the side with mass 3. So we should expect that the center of mass for the system will be on the M3 side of the triangle. And that means that everything on this side is now out. We will no longer consider that portion. Then we'll go to mass 2. And we will bisect the triangle once again, or try to bisect it here. By bisecting the triangle this way, we've removed mass 2 from the argument, and we have to ask ourselves, which side of this cut should the center of mass be on? Should it be on the side with mass 1 or the side with mass 3? And again, it should be the side with mass 3, because mass 3 is bigger than mass 1, and that means we get to discount this area. One last time, we'll take mass 3, we'll bisect it, passing through the triangle. And which side of this bisector should we expect the center of mass to be on? The side with mass 1 or the side with mass 2? And it should be the side with mass 2, because mass 2 is bigger than mass 1, and that means that everything in here is out. So we've narrowed down the range considerably, but there's still quite a bit of area inside this smaller triangle where the center of mass for the system could be. I'm only going to use this as what I refer to as a guesstimate. So I'm guessing / estimating where the center of mass for the system should be. And now we're going to let the math take over. And if the mathematical solution that I get ends up somewhere inside this yellow highlighted area, then I'll be fairly confident that I have the right answer for the center of mass of this system. All right, so we said we're going to let the math take over. What does that mean? Well, if you notice, when I drew all of these bisector lines, they all kind of crossed at a central point in the triangle. And that would be the geometric center of the system. That would be where the center of mass would be located if all 3 of the masses were equal in value. But as we know, they're not. When we look for a center point, imagine you were looking for a central point on a data set. Well, for the central point on a data set, you would just look for an average. You would take all the numbers, you would add them together, and then you would divide by the number of terms that you have, and the average should be the value that is right in the middle of all of the other values. Well, that's what we would get if we averaged together all of the ordered pairs of our masses. We would get an ordered pair that relates back to the center point. But each ordered pair is affected by the amount of mass that is located at those locations. And so we have to update our averaging technique. We can't just take a direct average of the locations of these masses. We also have to assign some contribution that each mass makes to the total system. And the way that we can do that is to use what is called a weighted average. And this is probably something that you've had in another class at some point. You may have had a teacher or a professor say, all right, we're going to have 1,000 points worth of homework problems, but all of those homework problems are only going to contribute to 25% of your total grade. And then we might have 2 tests during the semester. Each test will be worth 100 points each, but those will contribute to 50% of your final grade. And then you might have a couple of projects that are worth 50 points each. So maybe you have 3 projects worth 50 points each, and that'll be the remaining 25% of your grade. So each grouping of assignments, whether it's homework, test, project, has a certain point value associated with it, but then those points are weighed against the total. That's what we have to do with these masses in the system. We have to weigh the contribution of each mass to the total distribution of mass in the system. And here's how we do that. We're going to start by working in one direction at a time. We're going to start by working in the x direction. And I just want to know where along the x-axis should the center of mass for our system be. Then I'll come back and I'll ask the same question for the y-axis, and our center of mass will have an ordered pair that describes where the center of mass needs to go. But we need to do this one axis at a time. So we'll start with mass 1, and we'll ask ourselves, where is mass 1 on the x-axis? Well, mass 1 has an x value associated with it. We'll add that to the x value of mass 2, and then we'll add that to the x value of mass 3. And this is the first step in any kind of averaging process. We have to add things up. But the next thing we have to do is we have to weigh the contribution of each mass at those specific locations. And the way that we can do that is to multiply each position value by the mass that is sitting there. So mass 1 will be multiplied against its value on the x-axis. Mass 2 will be multiplied by its x value. And mass 3 will be multiplied by its x value. The next step is to divide. Well, what are we going to divide by? We can't just divide by the number of terms. It would make sense to divide by 3. But if we do that, we get the wrong units. I'm looking for a location on the x-axis where my center of mass needs to be located. So I need the units to be in, I guess we've decided meters here. But everything that I have in the summation so far says that I have kilogram meters for all of my terms. The only way to get back to just meters is if I divide by kilograms. That's what I need to do next. I need to divide by a mass, And that mass is going to be the total mass of the system. Why is it the total mass? And how does that benefit us? Well, every term now has to be divided by the total mass. Mass 1 divided by the total mass tells me what percentage mass 1 contributes to the system. Mass 2 divided by the total mass tells me what percentage mass 2 contributes to the system. And mass 3 divided by the total mass tells me what percentage mass 3 contributes to the total system. So let's take a moment and just look at those mass values. We have 1, 2, and 3. So obviously the total mass of the system is going to be 6. We have 1 over 6, we have 2 over 6, and we have 3 over 6. What happens when you add all of those values together? Well, I end up with 6 over 6, or 100%. So this approach does, in fact, keep track of the individual contributions compared to the total, which has to be 100%. We're now going to match those ratios to the individual positions that each mass occupies. Now I'm gonna rewrite this expression because we want center of mass x component. So what are we doing in this top line here? Well, we have a summation of each individual mass times its individual position on the x-axis. And we can simplify that by writing it out as a summation. We have the summation of each individual mass times its individual position on the x-axis, and we continue that summation until we've accounted for all masses in the system. The reason we want to write this in this more general form is because we're not just going to limit ourselves to 3 masses. We could have millions of particles in a given system. And then in the denominator, well, what do we have in the denominator? Well, we just have the total mass of the system. How do you get the total mass of the system? Well, you add up all the masses in the system. Now, you might be tempted to take that summation of masses in the denominator and that summation of masses in the numerator and divide them out, but that's bad algebra. This is the summation of the product. It is not the product of the summations, and there is a distinction between the two. If we were to cancel out the masses, all you would have left would be the sum of the individual positions. And let's see what that would do in the case of the x-axis. If I added up all the individual x values, we've got 0 plus 2 plus 8, that would be 10. And that would mean that my center of mass would be out here somewhere. And we know that that's not true. So we're not going to, oops. I'll just hit the back button here. If it'll let me. There we go. So we have to leave this equation as is. But this equation will tell me where on the x-axis the center of mass needs to go. So let's try that. Let's put everything together in the equation that we've made up here. We need mass 1 times its position on the x-axis. Mass 1 was 1 kilogram. The x value of mass 1 was at the origin, so that's 0. Then we need mass 2, 2 kilograms. The x position of mass 2 will come up here. And, oops, that was 2. So we'll put in a 2. Plus mass 3 times the x position of mass 3. Mass 3 had an x value of 8. All that needs to be divided by the total mass of 6 kilograms. We have 0 plus 4 plus 24 over 6. That's 28 over 6. And let's see here. I'm just going to plug this into my calculator and get a decimal value. 28 divided by 6 is 4.67. Now the units of everything, if you remember on the top we had units of kilogram meters. In the bottom we should just have kilograms. So we're getting units in meters, which is what we wanted because we want to measure along the x-axis how far do we have to go until we get to the center of mass for the system. And it says that we have to go out to a value of 4.67. So 1, 2, 3, 4, a little bit past 4.5 would be 4.67. And so the center of mass for this system has to be somewhere on that line. So our center of mass x value is 4.67. We're going to go back and we're going to do the same thing for the y-axis. Now for the y-axis, this is fairly straightforward because we've already done all of the arguing. Just because we're on y-axis doesn't mean that the math is going to behave any different. We now need to look at each mass and where it is located with respect to the y-axis. And that means that our center of mass expression for the y-axis would be the sum of each individual mass times its individual position on the y-axis divided by the sum of all masses. Mass 1 was 1. The y value of mass 1 was at the origin, so that's 0. Mass 2 was 2. Mass 2 had a y component of 6. Mass 3 was 3 kilograms, and it had a y component of 3. All divided by 6. And in this case, we have 0 plus 12 plus 9 all over 6. So 12 and 9 makes 21 over 6. 21 over 6 reduces to 3.5. So at the point y equals 3.5 is where the center of mass for the system needs to be. And we'll come up to 1, 2, 3.5 right there. Center of mass y component 3.5. And where those two cross is where the center of mass for the system will be located. And that center of mass now has an ordered pair equal to 4.67 I hat. Well, actually, let's not do I hat. We'll just keep it an ordered pair notation. And so that's where the center of mass of the system exists. What we can now do is we can take those three masses out of the system. We can remove everything. Mass 1, mass 2, mass 3. And we can replace them with one equivalent mass placed at that location of 4.6, 3.5. And that equivalent mass value will have to be equal to the total mass of the system. This is why we want to find the center of mass for a given system, is so that we can now do all of our physics with just the one mass as opposed to trying to keep track of multiple masses at the same time. This all sounds well and good, except that it took us a bit of time to go through and calculate where the center of mass for the system needs to be with respect to all of those other masses. Now it is worth mentioning here that in the real world is 3D, and so what happens if you have a z-axis? Well, then we'll just replace the x's or the y's with z components. And now we have a center of mass expression that will tell us where the center of mass needs to be located on the z-axis. But it's just the same equation written out 3 times. We just switch out the appropriate variable for the x, the y, and the z-axes. All right. So now we know where the center of mass for this system of particles is going to be located. What happens if those particles then start to move? So if mass 1, oops, got to switch off the eraser function. There we go. What if mass 1 is moving? What if mass 2 is moving? What if mass 3 is moving? So now each of those masses has a velocity that is going to carry it away. If the individual particles move, what does that say about the center of mass for the system? Okay, well, I'm gonna slightly change the notation that I have here. Instead of saying center of mass x, I'm going to say x component center of mass, and I'll do the same thing for y and z, because this is going to make our future work a bit easier to follow. Well, consider that all the masses in this system are now moving around. Mass 1 is moving, mass 2 is moving, mass 3 is moving. So, can we say that each mass is changing its position along the x-axis if they're moving? And the answer is yes. Each mass could have some change in its value along the x-axis as it moves through space. Is it possible that each mass could be changing its position along the y-axis? Again, yes, that is a possibility. Is it possible they could be changing their position along the z-axis? Yes, they could. Well, if each mass can potentially change its position along the x-axis, then what does that mean in terms of the weighted average expression that we've already come up with? As far as the algebra is concerned, I've introduced a delta statement to all of the individual x values of my particles. And algebraically, what we do to one side of the equation, we have to do to the other. And so now we have an expression here that tells us how the center of mass in the system will change as each individual particle changes its position. And then we can take that idea and we can run with it, because now going from the x-axis to the y-axis to the z-axis, all that requires is that we change the variable that we're using in our expression. We're going to see the same equation written 3 times, once for each axes, x, y, and z. And so now we can map out how each individual mass will change its position, and that will tell us how the center of mass for the entire system will change as a whole. Okay. What next? Well, we know that if these particles are going to change their position, there has to be some velocity associated with those particles. If each particle has its own individual velocity, can we relate that to the velocity that the center of mass for the system will have? And again, the answer is yes. It's a fairly straightforward fix. In getting from this equation to this equation, we introduce the delta statements. Well, now I need to go from a delta statement to a velocity statement. Back the first day of class, we defined what velocity was, and we said that that was a change in position with respect to time. Okay, we can do this. I already have a displacement term. If I divide that by time, then what I get is a statement that says your center of mass is changing its position along the x-axis in a given time interval. Because we're only on the x-axis, that means that we have the velocity of the center of mass as it travels along the x-axis. What I have to do next, algebraically, what we do to one side, we have to do to the other, and so I need to divide the other side by time as well. But this is actually to our advantage, because we already said that each mass should be moving with its own individual velocity, and that's what this next combination tells us. We have a change in position over a change in time for each individual mass. And that means that we will have the x component of velocity for each individual mass as a part of the total summation. And now we know what the x component of velocity for the center of mass will be. I apologize, I know that there are a lot of subscripts that are popping up here, but we really have to be careful and specific in the labeling process. But at this point, you can very easily rewrite this equation for the y-axis. All we have to do is replace all the x's with y's, and we're done. Then we can rewrite the expression for the z-axis. All we'd have to do is replace the x's or the y's with z's. and we would be done. So there's our center of mass, y component of velocity. I'm not gonna write out the z component because at this point I think you can do it on your own. But then what comes after velocity? Well, after velocity comes acceleration. And trying to get this to move over, I'm going to have to draw a couple little marks on the page here so it'll let me. There we go. Well, next comes acceleration. How do we get acceleration? We have to have a change in velocity with respect to time. Just like the position. If position can change just by introducing a delta, there's no reason that velocity can't change just by introducing a delta. The next step will be to divide both sides of the expression by time. And what that makes for us is the x component of the center of mass acceleration equal to the x component of each individual mass acceleration as a part of the summation expression. And now we have an equation for the x component of our center of mass acceleration. We can then reproduce that process to find the center of mass y component of acceleration. We would need each individual y component accelerations. And then again, if you needed a z component, you could very easily reproduce that. If you need to, just replace your y's with z's. But taking a step back here, it's not wanting to let me zoom out. Okay, well, we've basically got the same equation. We've got a summation of each individual mass times its individual, fill in the blank, either position, displacement, velocity, time, but it's the same equation again and again and again. If you can remember this equation, then you can very easily adapt it to the y and the z direction. You can also very easily adapt it for changes in time, changes in position, changes in velocity, until you have accounted for every possible center of mass equation that is out there. Well, again, why are these helpful to us? Why is it worth knowing where the center of mass of the system is located? Why is it worth knowing how the center of mass for the system is moving? And by the way, for something like, let's say, center of mass velocity, to get rid of these here, so we want center of mass velocity. So center of mass velocity has up to 3 components, x, y, z. Remember, velocity is a vector. But each of these is only a component. This is just the x component of the center of mass velocity. This is just the y component. This is just the z component. If I want to know the full center of mass velocity, well, then we have to put those together in component form. To produce the full three-dimensional vector. All right, so there was a sigh there, because even though the math for finding all of these center of mass terms seems pretty straightforward. The real hurdle is actually getting through those summations. Up here we only had 3 particles in our system. And we said, oh, that's no problem. We can do a summation with 3 particles. Easy. But what happens when you have a system with 100 particles, 1,000, 1,000,000, 1,000,000,000? We don't have time to sit around and do those summations. But could you take any one of these equations that we just came up with and put them into a computer program, like Excel or some other simulation software, and then tell that program, here's a data set. Maybe you import that data set from some other computer, and you have the computer do these summations for you. That's the real power behind these expressions. We want to take systems that have hundreds of thousands, if not millions and billions of particles. We want to let the computer condense all of that into a single equivalent mass that moves around with these terms that we're calling center of mass location, center of mass velocity, center of mass acceleration. The benefit to doing this: let's say I want to know the total kinetic energy in a system of particles, and that system involves 20,000 different particles. Well, I guess we better get started. We'll take 1/2 mass 1, velocity 1 squared, 1/2 mass 2, velocity 2 squared, all the way out to the 20,000th mass. Well, no, that's going to take too long. Instead, what's happening here when we add up all these terms? I'm going to put in one more term just for the sake of seeing what's happening. Well, we have a summation going on that involves 1/2 times the sum of all the masses in the system times all the individual masses squared. Would it not be easier to just find out what the equivalent mass of the system is, which in honesty would just be the sum of all the masses in the system, and then apply that to the velocity of the center of mass for the system and call it good? And in fact, this process here will condense down to the same equation that we have right there. The reason that we would prefer to do it this way is because this keeps the terms separate from one another. We can find the center of mass velocity separate from the total mass of the system. What we cannot do is we cannot separate these individual values. And if I already know the center of mass velocity, I can rather easily go back and forth to things like change in position for center of mass and acceleration center of mass, which I cannot do up here. As for the center of mass acceleration, if I know how the total mass in the system is going to accelerate based on that center of mass acceleration, well, mass times acceleration, that's force. But what force is this? Well, there was such a thing as a sum of forces, where we took all the forces in the system and we added them up. So mass 1, acceleration 1, mass 2, acceleration 2, mass 3, acceleration 3. Messed that one up. acceleration 3, on and on and on. So this is just the sum of each individual mass times its individual acceleration. And that would be the net force in the system. Or could we just as easily take the total mass of the system and combine it with the center of mass acceleration and call that good as well? And the answer is yes, we can. Because this means that once the net force is known, we can start doing things like solving for net work, which in turn is responsible for any change in kinetic energy for the system, which in turn, can't get my screen to move, here we go, which in turn would be responsible for any changes in kinetic energy for the system. So center of mass is really just a shorthand method of taking a very large system of masses, condensing it down into a single expression that then allows us to go back and forth between all the different types of physics that we've been doing, like velocity, kinetic energy, work, force, because we don't want to be here adding up millions and millions of different terms all the time. We'd rather let the computer do that. You're not going to have problems like that in your homework or on the tests. I'm not expecting you to do any of these homework problems on Excel or some other math program. For the center of mass problems, you may have 3, 4, or 5 different particles, and I want you to find one of the given terms up here that we've defined, whether it's position, velocity, acceleration, etc. But at some point we will have to graduate up to a system that does have a very large amount of particles. And those systems that have lots and lots and lots of particles, systems that we don't want to hang around and waste a lot of time on summations, are going to be these macroscopic objects. So here I've got something that looks like a brick, and that brick is made up of billions and billions and billions of atoms, and I want to know where the center of mass of that brick is. So start your summation, and you might be thinking, well, doesn't it make a lot more sense that the center of mass for this brick would just be at its center? Do we really have to go through and do all this summation stuff? And the answer is no, we don't have to do this. There's actually a way that we can take advantage of the symmetry of these systems and completely bypass all of this summation stuff. And that's what we're going to look at in the next video. So we'll see you back for part 2 of chapter 9.